In this video, we'll demystify K-means, the workhorse of unsupervised learning. By the end, you'll understand how K-means groups unlabeled data, why initialization matters so much, and how to choose K, and the traps to avoid, especially in higher dimensions. Welcome to AI Club Pro, where we make AI concepts feel like everyday ideas. To provide a quick context, when we talk about K-means, we are essentially in the unsupervised learning area. There are no labels. We are not predicting a price or a category. Instead, we are discovering structure, natural groupings in the data. K-means does this by partitioning data into K clusters, each summarized by a centroid, the average of its members. Intuitively, K-means asks, what points naturally go together? If you give me K, the number of groups, I'll place K centroids, assign each point to its nearest centroid, move centroids to the average of their assigned points, and repeat until nothing changes. That's the gist of how K-means functions. We'll use a customer segmentation toy dataset so that it's visual and relatable. So let's assume that your dataset has two columns, the annual spend, which is in thousands of dollars, and the visit frequency, which is the number of visits per month. So here's how K-means would work if you want to cluster this data. K-means minimizes the within cluster sum of squares, also known as inertia, represented by the formula that you see on the screen. The C_K here that you see is the set of points in cluster K, and mu_K is the centroid of the cluster. So K-means works in two alternating steps. It progresses by iteratively going over these two steps. So the first step is where it updates the assignments of all the points that belong to a centroid as one step. In the second step, it calculates the centroid based on all the points that are assigned to a cluster. This causes a shift in the centroid location. And since the centroid location has shifted, it has to recalculate step 1 to assign points and then again proceed to step 2. This goes on for a certain number of iterations till convergence is achieved. We say convergence is achieved when the cluster assignments stop changing from one iteration to the next, or equivalently when the centroid positions stabilize and move less than a very small threshold. At that point, algorithm has reached a steady state. Further updates don't improve the solution. Notice here that the cluster names are human given. K-means just finds the groups and we interpret and name them. That brings us to the next question of initializing these centroids. Initialization has a huge role to play in clustering. K-means can get stuck in a local optimum if you don't initialize well. Where you start the centroids changes where you end up. So in 2 dimensions, we can see good versus bad starts, right? But in higher dimensions, we can't. So seeds are often random. A widely used improvement is K-means ++, where you pick the first centroid at random and then pick each next centroid with a probability that is proportional to the squared distance from the nearest chosen centroid. This spreads out and reduces the bad starts. It's the default in many libraries. If you're not sure about your solution, you can run K-means multiple times with different seeds and keep the solution with the lowest inertia. Also note that clustering is very often not unique. If you weight spend more than visits, or if you standardize differently, you get different but valid groupings. That's normal. Clustering reflects your perspective and purpose. You can use the K-means algorithm in several unsupervised use cases. For example, customer or product segmentation for targeted campaigns, or prototype discovery, where you compress the data into k representative centroids, or anomaly detection, where essentially the distance to the centroid is a rough score. So if the score is really high, then it's probably an anomaly. Or initialization of other more complex models like Gaussian mixture models. This brings us to the next question. How does one choose k for a given dataset? You're essentially balancing two goals. One is tight clusters, which is the points are close to their own centroid, and the other is separated clusters. The clusters are far away from each other. So if you have a k that's too small, the clusters are bloated. And if you have a k that's too large, then the clusters fragment into noise. So to address this, we'll go over a bunch of approaches that help you with choosing a value of k. So the first method we'll go over is the elbow method. This method measures the total within cluster variance, also known as inertia or sum of squared errors. As k increases, the sum of squared errors always decreases. We look for the elbow, the point after which adding clusters only improves this sum of squared error by a little bit. Elbows can be subtle or ambiguous. Treat them as a first pass, but not the only criteria based on which you select your k. Use the needle or the knee finding heuristic if you want an automated elbow detection. The second approach is the silhouette score. So the intuition is that for each point, you compare how close it is to its own cluster versus the next best cluster. So you have a few variables in order to understand the equation for the silhouette score. So a underscore I is the average distance from the point I to the points in its cluster, right? And b underscore I is the minimum average distance from point A to points in any other cluster. So that measures separation. And the formula that you see on the screen is how you calculate silhouette score. So here's a rough interpretation of the silhouette score. If the score is between 0.7 and 1, then you have very clear clusters. If it's above 0.4, then you can say that it has a reasonable structure, but anything below that is pretty weak. Also note that the silhouette score uses distance, so you should scale features before you rely on it. And it works best when the clusters are roughly convex or spherical, because that's a hidden assumption that k-means makes about the data points. Another really good statistic is the gap statistic. So the idea is that you compare your clustering quality to what you'd get from no structure. So if points were to, for example, be drawn from a uniform reference within the same bounding box. So what you do is you compute your log of within cluster dispersion using the formula that you see on the screen. You generate B reference datasets uniformly, and then you compute their log of within cluster dispersion, and you take the mean of that. And then essentially you calculate the gap and pick the k with the largest gap or the smallest k using the criteria shown on the screen. So this is a great sanity check against seeing clusters in clouds, but it does need multiple simulations. So it's all right for offline analysis. So essentially when you use k-means, something that you should be doing is scaling your features and then running it with a bunch of k's, like for example k from 2 to 10 or something like that, depending on what your application is, and initialize it with a good algorithm like k-means plus, right? And then plot the elbow and the silhouette scores for all the different k values and check if they make sense. Use the gap statistic if you're able to do this offline, and that would more or less get you to a place where you can get k-means to work for you. So if you think about some of the practical considerations, a few things that you need to keep in mind, they are that you need to scale your features, you need to standardize or normalize them so that scale doesn't dominate the distance calculation. If it's too complex, you have a very large n, then try using mini batch k-means. If you have a situation where you get some empty clusters, then catch those and reseed the empty centroid to the farthest point or split the largest cluster. Also note that k-means is very sensitive to outliers because it essentially calculates the mean and it's pulled by the outliers. So you could use certain techniques like k-medioids or trimmed k-means so that you reduce the impact of outliers. Also note that k-means assumes that your data is more or less spherical and has more or less equal sized clusters. If this is not the case, then you shouldn't be using k-means. There are other clustering techniques like spectral clustering, etc., which is what you should be using. And if you have data that is very, very high dimensional and distances are becoming less informative, then you should use PCA or autoencoders to reduce the dimensions before using k-means on them. So in summary, k-means is simple, fast, and surprisingly powerful when you scale your features. You need to choose your k thoughtfully and seed well. Remember that clustering is unsupervised and there isn't just one right answer. Your business context and data preparation define what good looks like. So that's a wrap. Thanks for joining us on AI Club Pro. Hit that subscribe button for more eye-opening AI stories and insights. Stay curious and keep exploring.